It is 2 hours UTC, time for Astronomy Daily Live. Hey, everybody. You can call me Cosmic, and welcome again to this ever growing circle of friends who share a common passion for the science of astronomy. So, hope everybody's doing well. You know, one of my pet peeves with other YouTube um, live streamers is that they seem to sit and wait until they see their live stream going. And so they'll sit there for 20 seconds or 30 seconds just when as soon now look, I am new to this, right? I'm new to this. But I know that when I hit that start broadcast button and it says I'm live, I I'm on, right? I'm on. I don't wait until I see my live stream happening because I know that there's a delay, right? So look, it's just one of my little silly little peeves that uh I don't know, just bothers me. It's sort of like you know, don't you realize that as soon as you hit that that live button, um, we're a go? I don't know. I don't know. That just seems sort of a rational, intelligent thing to me. Speaking of being rational and intelligent, I am going to tweet the fact that I am on live now. Doink. Gonna do it. Uncle Bill, see, I'm doing my job. I'm doing my job. Now, the other thing that I want to do is pop my chat out. I've already paused it. I've already paused it, so it's not going to freeze my Linux machine. I'm going to pop out the chat. I'm going to go over here to my smartphone and start up the live stream so I can just monitor it and make sure that it isn't being too silly. Um, so yes, I remembered. Dun, 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 dun. Yes, yes, and I guarantee that I will not always remember. so, so yeah, hope everybody's doing well. We had a successful launch of TESS. I always forget what that it's the transit the the uh, I'm gonna get it here. Google. Google is my friend. Uh, test, test launch, test launch, test launch. The transiting exoplanet survey satellite. It's like a washing machine size um, uh, device that has, I think, 4 telescopes on it. I should know more of the details about that so I can sound moderately intelligent when I talk about it. But um, it's for those of you who don't know, TESS was just launched a couple hours ago from a Falcon 9 rocket in Florida, and launch went well. It was a nice boring launch. Um, First stage landed on a drone ship. Of course, I still love you, out in the Atlantic Ocean, and the second stage fired for a little while, shut that down. TESS was successfully deployed. I just heard some tweets a little while ago that the solar panels are out. So yeah, looks like that was a successful deployment. Now it's up to the spacecraft itself, and the awesome um, um, uh, um, engineers and scientists on the ground to sort of get it into its proper orbit so it can start doing its work. Now, just my opinion again, I think that tests and searching for um, um, extrasolar planets, I think is really, really, really awesome. But like a lot of things, I haven't really studied it too closely enough to really have a good grasp of some of the basic stuff. Um, and there are two things that sort of stick out with me in terms of detecting so-called extrasolar planets by the transit method. Okay, this transit method is this idea that uh, you measure the brightness of a star, right? It's photometry. Okay, that's all it is. It's just measuring the brightness of a star, sort of not necessarily continuously, but often, right? Um, and the idea is that if it just so happens that the the um, uh, the orbit of a planet going around that star makes it such that from our vantage point, it appears to pass in front of that star. That's what's called a transit. It's also called, yeah, I don't know if I would call it an occultation. I guess you'd call it an occultation as well. There's a bunch of different names for these things. I would call an occultation more like a blocking out of the light. And a transit is for sure a blocking out of the light, but most of the light you're still seeing the star. So, um, but if this planet is such that from our point of view, it um, it appears to transit the the star, right? Then what can happen is that the measured brightness of that star can go down a little bit. It can dim a little bit. Now that depends on the apparent size of this planet, right? Um, if it's well, and of course the apparent size of the star itself. Now the apparent sizes of of all stars are in micro arc seconds. So they're really, 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 really small. So we can't actually see this transit take place. But supposedly we can see that the star's brightness dims a little bit for a small period of time, minutes or hours or days. Um, I think the way that we're looking at things now, like with the Kepler spacecraft and other telescopes here on Earth, which is one of the questions that I have. Um, uh, uh, anyway, we'll see that. Now, one of the things that has sort of bothered me about the transit method is that a lot of ground-based observations are now doing it, and I don't exactly know why it took Kepler to say that star uh, has a transiting event, and then our ground-based telescopes can go and see those things. I'm not quite sure why it takes um, something else to point that out. If our ground-based telescopes are fully capable of being accurate and precise enough in their photometric measurements to be able to see those kinds of things, why can't we see those things a lot more? Don't know. Don't know. The other things that bother me about exoplanet discoveries is, um, you know, these planets, the orbits of these planets have to be, um, uh, very much in line with our sort of line of sight. And I don't know, there seems to be a lot of planets that line up that way, a lot of exoplanets, that line up that way, and that just seems to me to be a little strange. Um, who are you, and what did you do to Cosmic? I don't know. I don't know. um, so I'm you know, it's the skeptic in me, right? It's the skeptic that says, it's like, hmm, why are we finding thousands and thousands and thousands of these so-called um, exoplanets when the alignment has to be so absolutely perfect, right? In order to see them at all. There seems to be quite a few, and again, I haven't really looked at this hard enough to be able uh, to answer these. So I'm just sort of throwing these out, as thoughts, and very, very, very likely. It's very, very, very likely there are some both simple and reasonable explanations for um, for these questions that I have, and so um, you know maybe you know uh, yeah, I just don't have an explanation for that one, that I can come up with on the top of my head. Why can we see so many of these when a transit is so incredibly rare? It's so unlikely to happen. Why are we seeing so many of them? I don't know. And something that sort of ties in to that is sort of my my third thing, is that I'm not exactly sure. And again, I think just a review of the process would probably um, um, illuminate this. But how do they account for false positive? What makes a false positive? How do you know that you have a false positive? Don't know. Don't know. Yeah, Tom, I totally agree. It's probably a numbers game, and it's just, the um, probability of that kind of alignment happening is extremely low. But if you have thousands, millions, billions of these planets, maybe seeing quote unquote only a few thousand of them, maybe that makes sense. I don't know, but I mean, we're basically relying on Kepler, which I think Kepler, I don't know how many stars Kepler uh, looked at and monitored. Um, I don't know. I don't know. See, there's a lot of things that I just don't know, and um, um, probably if I took the time to investigate it myself, or ask the right people the right kinds of questions, I could get those um, answers. I'm just I'm being I'm being a scientist, and I'm being extremely skeptical, um, but also, of course, um, open-minded. So I'm completely open to any plausible and reasonable um, explanation. Cheers. Hydrogen hydroxide tonight. HOH. Cheers. And and uh, I guess I'm not as excited about discovering exoplanets as many are. Um, to me, the existence of planets around other stars isn't that much of a surprise. Just like life, for me, is not the discovery of life um, elsewhere isn't going to be. I mean, it's very cool. Okay, don't get me wrong, right? It's very cool, but I'm not surprised that there are planets around other stars. I'm just not, and so I'm just not. I'm not as excited. Everybody seems to be hyperventilating over this, this idea that there are planets around other stars. And it's like, to me, it's sort of a no-brainer. I don't know. I mean, it's very cool, right? But I don't know. And as far as life goes, what why why do astronomers care about life? Isn't that like what biologists are excited about? I don't know. You know, astrobiologists, right? That's sort of a new field. There are supposedly astrobiologists now, and I don't know what they do, because there's no data. so so but there will be, for sure. So once we establish that life is plentiful and actually pretty easy, um, then the astrobiologists will have a real job. But until then, they can model, they can guess, they can speculate all they want. And as I said, I'm not quite sure why an astronomer would necessarily be interested in life, or the discovery of life. Um, uh, that's biology. That's not really astronomy. Um, so yeah, again, that's just me being uh, uh, being sort of the anti crowd person, and yeah, you know, to me, planets around other stars and life uh, not on Earth is pretty much a no-brainer. It's just sorry about the itchy nose. Um, to me, it's just a matter of time uh, until we find life, and it's going to be surprising, and it's going to be very cool, and I think it's going to change. It's going to change a lot of people's perspectives on things. As I said, I've already made that leap. So um, life seems to be it seems to be pretty easy. Um, So yeah, I just don't see it as a big deal at all. So yeah, okay, all right. Hey there, I don't know how to pronounce your big long name, so you're gonna have to sound it out for me. It's hepta. Oh man, I don't know, but welcome. Glad you're here. We talk astronomy here for a while, a while. 30 minutes to an hour or so. It's all about the astronomy. So welcome. Glad you're here. Uh, yeah. So hope everybody's doing well. This is Astronomy Daily Live. Glad you could come in. Um, a raptor that is both spectacular and hip. Yeah. Okay. Hip hip. Oh. All right. I will call you hip because that's about as much. That's about as much as this little brain can wrap around that awesome name. So yeah, glad you're here. Glad you could stop in. Stop in any time you want. That's one of the really cool things about having a daily live stream at the same time, at the same place, is that you shouldn't feel obligated, to come in here every single day. Um, if you want to, please um, join um, um, the circle of friends. We share a common passion for everything, right? So come on in anytime you want, and yeah, glad you could stop in anytime. Welcome. Spread the word. Make sure to subscribe if you haven't already. Now, what we basically do here is just have a very casual conversation about astronomy. Um, um, Uncle Bill, one of our regulars, you're seeing him in the chat there. He says that we nerd out, and yes, absolutely, that's what we do. If it wasn't for the nerds, uh, we would definitely not have what we have now. It's called the triumph of the nerds, and yeah, so we totally nerd out here about all things astronomy. We throw in a bunch of science. Um, yeah, very cool. Yeah. So let's see. I think what I want to do, I think what I want to do is I want to dive into this paper that just came out on archive.org, and it's a discovery. It's a discovery of something new, and I think new things are very cool, very cool, because I mean, right, for no other reason but because of the novelty, right? It's just new. It's new. And we humans love new things, new things. But on top of that, what new stuff does, especially when it comes to science, right, is it adds more information. It adds new data uh, to our already existing database, um, and maybe throws in a curveball, or maybe, sort of, cements ideas in a little bit more. It's like, okay, we have these ideas about whatever, right? And then we make a new discovery, and it's going to fit into some slot, right? It might be a brand new slot, but it's going to fit into some kind of slot somewhere, and that is going to help us, hopefully, understand or give us a different perspective on things. It's the Hip and Uncle Hype team. Yeah. All right, I'm gonna pause just for a second because I have to be doorman. Okay, one of my roles in life is doorman to kitties. So I will be right back in like 10 seconds. Hold on one sec. All right, we are cool. We are cool. Um, you you smell like a nerd, and you're coming with us. Yes, yes. But you know, as I said, this is a circle of friends. It's just like, I mean, how I sort of see this, right, is that we're all sitting on the back porch under the night sky, some kind of an awning, maybe, but we can see, the dark sky, and we all sit down in our comfy chairs, and we, turn off the TV, forget about the news, and we think astronomy. We think about a common passion for a little while every single day. And it's so cool that we can do this in sort of a virtual way. It doesn't matter where we are, either on or off planet, right? We we can come together um, in this way and just share a common passion. And I think it's very cool. Anyway, let's talk about this new. I've got an itchy nose tonight. I apologize. Sometimes it's itchy nose night, and this must be one of them. So what I'm going to do is I'm going to share my screen. Now, if you don't know about archive.org, you need to check out archive.org. Okay, archive.org is a is um, uh, and let's just go over there because I cannot say more about archive.org. So that's arxiv.org, archive.org. And this is just the bleeding edge of not only, physics and math, computer science, biology, finance, stats, electrical engineering, and economics. Okay, covers them all. So usually how these are professional papers that typically have just been accepted for publication. So they haven't been published yet, but they're getting ready to be. It's usually called a preprint. And so Cornell, who hosts this site, has been kind enough to just allow any old Yahoo um, to come in here and read the latest and greatest. And so I always go, of course, to the astrophysics section. And every single weekday, okay, Monday through Friday, at around 1 hour UTC or so, so like an hour before this live stream starts, they do a dump of all of the latest um, um, astronomical papers, right? And there's usually, 20 or 30 or 40 of these. And this is the bleeding edge of research and knowledge and all of that. And one of the cool things about these papers, right, is that not only are these sort of the latest and greatest stuff that is um, going on in all of these areas of study, but every single paper is sort of a launching point for you to, one, learn more about dozens of concepts, right? Dozens and dozens and dozens of ideas. The other thing that each one of these papers are is um, a history lesson. So they have references, right? So they talk about some kind of concept, and then they have a reference where you can learn more about, you know, whatever they're talking about in that little concept. And it goes back in time, and you can go back and back and back and back and back. So it's really an awesome resource. Anyway, I found this one paper. Um, let's see if I can find it here. There it is. Snake in the clouds. So I will click on this. Snake in the Clouds, a new nearby dwarf galaxy in the Magellanic Bridge. So here's the abstract, which is just a very, very, sort of brief description of what they're going to be talking about. Excuse me, I'm talking about in this paper, and this is the reporting of a discovery of a nearby um, dwarf galaxy lying right between the large and small Magellanic Clouds. Now, the large and small Magellanic Clouds, of course, are dwarf companion galaxies to the Milky Way. And we've known about the large and small Magellanic Clouds for a while, hence the name Magellanic, I assume. And this is again, just the names themselves is a lesson in history. Cheers. Um, so watch. Okay. Um, so the Magellanic Clouds were named after Magellan, who sailed around the world at least once. Um, did he make it all the way around once, or did he lose it somewhere along the way? I don't remember exactly, but the Magellanic Clouds uh, were named after him, I believe. Um, and there's a large one and a small one, and these are visible in the southern hemisphere. So if you live anywhere in the north, you can't see them. But if you live in the south, like in Australia or South America, or I think pretty much anywhere sort of below the equator of the Earth, you can pretty much see these guys. So I've never seen them. I hope to at some point. I probably never will. I have no plans, but I'd certainly like to. But anyway, right between these two dwarf galaxies, they have discovered a smaller dwarf galaxy. So they're saying that it's about 50 parsecs in size. So a parsec is about 3.26 light years. So this dwarf galaxy is about 150 light years across, and it's 28,000 parsecs from us and 24,000 parsecs from the large Magellanic Cloud. And yeah, you know, this kind of paper being a discovery paper is just going to sort of lay out what they've observed about it. So, you know, how far away it is, how big it is, how it's moving, what kind of stuff is in it, you know, that kind of stuff. But it's new, right? No one has ever sort of, you know, seen this before. So that makes it new. So you can click on the PDF link here and you can actually read the paper itself. Cha-ching, cha-ching, cha-ching. Sometimes it takes a little while for me to download. I've got a slow internet connection. It's amazing that I can live stream at all, but I can. So quite a few authors here. Ozwilski, hey, I know him. He's actually the, isn't he the, he's the director of Stewart Observatory now, isn't he? I don't know. We'll have to find out. Yeah, there's number 11 right there, Stewart Observatory, University of Arizona. Yay. So here's the abstract again, just a reiteration of that guy. So let's get into it a little bit here. This, you know, this live stream does not claim to dive incredibly deep into things. This is just, you know, sort of to give you an overview, a very, very, very brief and broad overview of whatever the subject matter is for today, right? Let's see. So there is no solution to the missing satellites problem if it is defined simply as a mismatch between the total count of Milky Way dwarf galaxies and the predicted number of dark matter halos capable of hosting a galaxy, since there is no problem. Once the observed number of the galactic satellites is scaled up to correct for the effects of detection efficiency, little inconsistency actually remains. Interesting. It requires that the vast majority of the galactic satellites have extremely low luminosities, but occupy a large amount of mass. So I think where they're going with this kind of thing is that they're saying that there has to be a lot of dark matter in order to make all this stuff go. So let's see, they're making the galaxy a unique place to provide crucial constraints on the theories of universal structure formation. As a result of the expansion of the discoveries, blah, 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 blah. Let's see. So around these clouds, a relatively unexplored portion of the sky that has the greatest potential to inform our understanding of both the satellites of the Magellanic satellites and the clouds live as a pair is the area directly between the LMC and the SMC. I guess the idea, the theory is that these two dwarf galaxies have sort of drug in these other dwarf galaxies, including this one, which they're calling what are they calling it? Hydra 1, Hydrus 1, Hydrus 1. Okay, so yeah, as I said, I'm just providing a very, very, very brief and general um, um, overview. This this is to sort of entice you in, to sort of wet your whistle a little bit. I'm not going to be able to claim to be able to explain a lot of this stuff. It goes way over my head, but I love it. I love it. So yeah, this is just to sort of talk astronomy, right? So they've used this instrument called DE-CAM, which is I think they're calling it the dark energy camera. Yeah, the dark energy camera. Um, and let's see, they observed this, I guess, in 2016 and 2017, at least according to how, I think I'm reading that right. And right, they're looking at the region between these two large and small Magellanic clouds. Um, the DE-CAM is a large 570 megapixel camera, 62 CCDs, giving combined area of 3 square degrees. So that's pretty exciting. So it's down at CTIO in Chile, using let's see, 6 different filters there: U, G, R, I, Z, and Y. So this is one of the cool things. They have this telescope and this instrument that is doing one thing, but it's collecting all this data, right? It's collecting all this data, and these guys are grabbing that data and extracting new information. So that's very, very cool. That's one of the cool things about TESS, right? Is that TESS, of course, is going to be looking for and detecting exoplanets, but much, much more than that, it's going to be collecting data, right? And um, 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 researchers and astronomers are going to be grabbing that data and looking for other stuff as well that has nothing to do with planets at all. And I think that's totally, totally awesome. Let's see, the primary data source for this paper was acquired. So all the data, right, that we're going to see here was collected over 2 nights, just 2 nights of data. Now imagine what you could do in 10 nights or 30 nights or 100 nights, right? This is 2 nights worth of data. Let's see. Images were taken in the GNR filters with exposure times ranging from 70 to 225 seconds, 60 to 110 in the R band. So on average in the survey, each sky location was covered by 3 individual exposures, and the total observed area was approximately 140 square degrees. So blah, 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 the pipeline processing, all that kind of stuff. So there it is. There's the mosaic data, and there circled in red is our little newly discovered dwarf galaxy. Very cool. I'm not going to do much more here. Let's just sort of go through this a little bit. What I like to do is I like to look at the pictures and sort of read the captions and see what's going on. You can see here's a color magnitude diagram, which is a lot like the Hertzsprung-Russell diagram. It gives you information about populations and what what sort of the stars in this new dwarf galaxies are doing. How are they evolving? What do they look like? So here's again, just a color magnitude diagram. So let's see, the left panel is background subtracted, and the right panel, okay, test diagram of background stars around. Okay, so they're calling these the stars that are sort of in the dwarf galaxy itself, and these are the stars that are outside of the dwarf galaxy. Foreground stars, background stars, not necessarily associated with what they think is this dwarf galaxy. So they've observed some variable stars. That's kind of cool. That allows them sometimes to get a feel for how far away it is. Perfect agreement with the recent discoveries. Spatial distribution. So there's sort of a zoomed in idea. This is showing right ascension, alpha, and declination, delta, here. So that is sky position. And I guess the black dots, let's see if it says the distribution of MSTO stars in the vicinity of the Hydrus 1 satellite. The dashed gray ellipse shows the best fit shape. The arrow in the left corner shows the direction of the large Magellanic Cloud's proper motion. And the dashed line is parallel to the line connecting the large Magellanic Cloud and the small Magellanic Cloud. See, red crosses show the locations of BHB candidate stars. I don't know what a BHB candidate star is. While the red stars indicate the location of some variable stars. Cool. So I assume that the black dots are the locations of stars themselves. So you can see there's a concentration here, of course, and that is the dwarf galaxy itself. Density profile. I assume that this is like number of stars per square arc minute. So yeah, it's not incredibly dense. This is the distance from the apparent center outward. So yeah, at its highest, right, we're seeing maybe three stars per square arc minute or so. Okay. It is a dwarf galaxy, so there's not going to be a lot of stars. So they've done spectroscopy on it as well. They've selected what they think are, some members to sort of get an idea of what they're made of. Spectral show, let's see, the leftmost panel of Figure 5 shows the spatial distribution of all 235 spectroscopic targets. Let's see, where's Figure 5? Figure 5 is coming up here, I guess. Let's see. Where's Figure 5? Here it is. Okay. Okay. So yeah, they're just, they're looking at these stars in different ways. Again, here's the location in the sky. This is a color magnitude diagram again. Yeah, there's so many ways, to look at data, right? I thought this table here was kind of an interesting table. It sort of gives you everything, right? So where it is in the sky, the RA and deck. Sorry, the RA just got hidden. So the half light radius. I think that's yeah, just where sort of half of the luminosity is gone. So that's 7.42 arc minutes. So not incredibly big. Ellipticity, it's pretty elliptical. Position angle, distance modulus gives us an idea about how far away it is. So yeah, 27.6 thousand parsecs. Radial velocity looks like it's moving sort of away from us, but it looks like it's moving towards our galaxy. I don't know what these other things are, the J factors. I don't know. I don't know what that is. Anyway, lots of info there. 235 observed stars, 117 have a signal to noise larger than 3. So that's not bad. Let's see, what's this? Spectroscopic measurements of individual stars greater than 3 or a radial velocity error less than 10 kilometers per second. Yeah, so, spectra, if you can look at the spectra of something, you can find out all kinds of stuff, right? Temperatures, gravities, and also what's called metallicity. How much in this case the ratio between iron and hydrogen. Now, this is a logarithmic scale, and you can also get a better idea about how bright it is. The magnitude. Pretty faint little stars here. 18th, 19th, 20th magnitude stars. Pretty faint. You need a big scope and long exposures to see those guys. And then these guys really, these authors, they really do a deep dive and look at every single bit of stuff that they possibly can. So there's absolutely no way that I can get into all this because I hardly understand it myself. So, but as I said, all of this is sort of a jumping off point. if you read a paper like this, even if you don't understand a word of it, right? What I always say is go look at the pictures. Go look at the pictures. You know, be a 5-year-old kid. Be a 3-year-old kid that can't understand what the words mean, but you look at the pictures, right? Start with the pictures, and you know, read the descriptions down here. See if that makes any sense at all. Um, Now, if it's so far over your head that you just are completely like not a clue, well, then this paper isn't for you, right? But if you can grab onto anything at all, then that's a starting point. So this is just looking at chemical abundances, as it says here. They're looking at carbon, magnesium, and iron. That's very cool. And see how much magnesium is in these stars. It's just mind blowing. All from spectra. So this is just one of the stars where I guess they have detected carbon, right? Lots and lots of carbon. So that's pretty cool. Don't know what that's all about. Line of sight velocities of Hydrus 1 stars versus position angle. Okay. Nature of Hydrus 1. While the nature of Hydrus 1 as a dwarf galaxy is established by its size, dark matter content, and internal metallicity um, distribution, in this section, we put Hydrus 1 in the context with other systems of similar structural and chemodynamical properties. See, if you just read these things, you'll just sound smart, right? So yeah, I'm not gonna get into this much. Plus, we're running out of time anyway. Don't want to bore you too much. Um, yeah, you're exactly right, Uncle Bill. If you really want to learn to swim, you have to put yourself into a situation where you have to swim. So and that's what a lot of these papers are, is sort of diving into the deep end and seeing what happens. And there there, there is nothing wrong with this stuff going completely over your head. Okay, I've been doing astronomy my entire life, at every single level, right? I mean, I'm a professional. I've done the amateur thing. I was new, right? And when I look at a paper like this, I am like a newborn babe, right? I am just, this is, this is over my head for sure. But there are pieces, right? There are pieces that I can grab, and it's like, oh, okay, I sort of understand that. And, you know, if, if nothing else, as I said, I haven't pointed them out. Let's that when we come across a reference here, reference. Okay, yeah. See, here's a bunch of them, right? So it says, what does it say here? It says, in recent years, some of the deepest searches and strongest constraints on annihilating dark matter have come from gamma ray observations of the Milky Way's dwarf spheroidal galaxies, and in particular from the ultra faint population revealed by deep sky surveys. And here's a bunch of references that are apparently referencing these deep sky surveys, right? So you can go to any of these. Let's just look at um, Ackerman et al. In 2015. Okay, so we go to Ackerman et al. 2015. We go to the end of the paper, and we can look at Ackerman et al. 2015, and there's a reference. So if we wanted to, okay, we could go to this paper, which hopefully is also freely available online, and we can read about what these authors did in the context of the what were they talking about? They were talking about um, now. Now we got to go all the way back here. We got to find where we were. Whoop, find where we were, and um, let's see. Were we up here? I don't remember where we were now. Dark matter annihilation. Yeah, here. So yeah, in terms of these deep sky surveys. So yeah, it's just it's it's just a way of getting into it and finding a hook and following your nose. And nobody is going to understand all of this stuff, right? I mean, that's why these authors are writing about it, because they at least have a pretty good understanding. But most astronomers are going to be just like you and me. We're going to understand a little bit of it, and if we want to understand more, we have to dive into it a little bit more. Dun, 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 dun. All right, well, cool. I think that I am going to, I love looking at all the pictures, right? And these guys are getting into chemistry. Wow. But then they have some conclusions, right? So this satellite is located between the large and small Magellanic Cloud at a particular distance. Pretty confirmed members. I'm sure there's a lot more than that. But it's hard. It's hard to confirm membership, right? Because you're looking at this incredibly dense field of stars. Which one is part of the dwarf galaxy, and which one is part of our galaxy? It's tough. It's a tough nut to crack. Spatial position and observed line of sight velocity, we find it highly plausible that Hydrus 1 is part of the Magellanic family of satellites. Cool. This one is a very promising target for dark matter annihilation searches. I have absolutely no idea what a dark matter annihilation search is. Don't have a clue. Rather metal poor. Yeah, awesome. Anyway, a new dwarf galaxy, Hydrus 1. Welcome to the family. Welcome to the family, Hydrus 1. All right, I'm going to stop sharing. And I'm going to pop back over here. Da-da-da-da. And I think I'm going to get out of here for now. Let's see. Yeah. The mothership calls. The mothership calls. Plus, I am absolutely starving. Haven't eaten much today at all. Just been too busy. It really sucks when that happens. So I'm gonna go make some dinner and enjoy the rest of the evening. Have a nice calm evening. Been doing some work on my project. Maybe I'll try to give you folks an update on that tomorrow. Yeah, I'll try to remember to do that. In the meantime, hope everybody has a great evening, a great day. Stay awesome. Keep your nerd up. And yeah. All right. I'm going to get out of here for now because the mothership is definitely calling. So I will say cheers and and if you haven't subscribed yet to this YouTube channel, make sure to do that. You can set your notifications so you can know exactly when I go live. But I'll tell you when I go live, 2 hours UTC every single day. Now, I say every single day, and that's a lie. That's a lie because once I was not here, I had to not do a live stream one time because I was doing something else. And I'm here to remind you that this coming April 22nd UTC, okay, April 22nd UTC, I am also not going to be doing a live stream because I have a musical gig that I will be playing and I won't be here. I won't be here at the appointed time. Now, maybe I really doubt it. I really doubt it. But maybe I will live stream from that event for a short amount of time. Maybe. It sort of depends on how things are going and all of that. But I'm a musician, so I play music to crowds, and hopefully they like it. And yeah, I think this is going to be a pretty exciting event anyway. So I'm going to get out of here for now. Peace, cheers, and I will see you tomorrow, 2 hours UTC on the spin in a little less than 23 hours from now. So yeah, hope everybody does well and peace out. Cheers.